Okay, let's continue our studies in risk measures. Section 3, it's a rather mathematical concept formulation via acceptance set. I will leave this part to you as extra reading. Obviously, I will not test you anything from this section, nor will SOA questions. So let's directly jump to section 4, value at risk. This section obviously is extremely important. You should expect some questions from this section on the exams. Here is a short history. At least one of the triggering events is the market crash of 1987. There's also recent financial crisis about 10 years ago, which motivated a lot of people to study systemic risk. Those are the, say, the triggering events. Because of this a huge crisis, and a lot of companies went bankrupt. So there is a need to somehow come up with a measurement on the business risk, right? So that's one of the reasons, or at least an important reason, why JP Morgan prepared a technical report in 1994, and then there's a special. It started with a small group within JP Morgan. Later on, it became an independent group called Risk Metrics. I think it was purchased by another company, somehow relatively recently, I think. VaR is also the standard of Basel II Accord. So this is the this was the standard in the industry before, because now people we have Basel III, 3.5. Those come up with different idea, but at least VaR was once upon a time the dominant risk measure. It is still commonly used, but no longer considered as the most appropriate one nowadays. Okay. So let's define VaR, or value at risk. It actually comes from a simple concept, quantiles, which we studied before, right? So let's start with an easy case. Let's start with a continuous random variable. So so that means the cumulative distribution function, CDF, is strictly increasing over 0 and 1. Okay, it's strictly increasing. I mean the value, not over domain, over the domain of X. So what I mean is, when you draw a graph, let me zoom up a little. So when you draw a graph, so let's say here's X. I draw a graph for non-negative random variable. Let's say it looks like this. This is 1. So it's a strictly increasing curve, right? It goes from 0 to 1. That's on the y-axis. On the x-axis, it's strictly increasing, which means for any x1 strictly less than x2, we have fx1 is less than fx2. Okay, that is the meaning of strictly increasing. Okay. In common words, we don't have flat part, right? It's strictly increasing. There's no flat part. So with that in mind, I can define it for any level which is between 0 and 1. Well, if you want, you can define 0 and 1. So you can with 0 and 1 included, but with 0, you know, it's the smallest value, right? With 1, it's either the maximum or the infinity. So, you know, those two are trivial cases. So that's why usually I put round bracket. That does not mean you cannot define for 0 or 1, right? It's because 0 and 1 are trivial cases, and they are uninteresting. So that's why I put the round bracket. Here, what I define is the quantile Q delta of X is a constant such that the CDF at this point equals the level you want. Here, level is delta. It's always between 0 and 1, right? That's because the range of F is between 0 and 1. So pick any value. Okay, so let's take this to be delta, the intersection, and then draw a vertical line. The intersection again on the x-axis is going to be the quantile. Or let me be consistent on notations. So it's the quantile at delta level of x. If there's no confusion, you can remove x if there's only one random variable. Okay. So according to this definition, quantile, delta quantile of a random variable is always well defined if this random variable is continuous, right? But what if this x is discrete or mixed? Meaning, what if the graph has flat part? So the question is, so let me draw another case. Let's say still, you know, start with 0. Okay, and let's say I jump to another point, and then I stay flat for some time, and then I jump again. Okay, and finally, you know, I go continuously when it's close to 1. Okay, this is a possible shape, right? So here I have 2. Well, you can call this x1, x2. I have 2 jump points, x1 and x2. Between x1 and x2, there's nothing. So you have one piece, continuous part from 0 to x1, and then I have 2 probability mass points at x1 and x2, but there's no density between x1 and 2. That's why, you know, it remains flat. Okay, and then again, there's nothing between x2 and x3. After x3, I have a continuous density, so you know it goes continuously for the last piece. So you know there are a few interesting things, right, of this case. So now I have many questions. So let me first let's call this delta 1. So if I pick this delta to be delta 1, then we have a huge question, right? We have the entire, so if delta equals delta 1, we have fx of x equals delta for all x between x1 and x2. Okay, x1 is included, x2 is not included. So now the question is, which point do we pick, right? Previously here, for any delta, there is a unique point, right? For any delta, there is a unique point on the x-axis such that the function value at this point equals the level you choose. But here I picked a special value, delta 1, which is one of the flat piece. Okay, since delta 1 equals this flat piece, any points on this line would make this equality satisfied, right? So now the question is, which one do we choose, right? We have infinitely many candidates, right, from this interval. Okay, that is one question. Okay, now let's look at another question. So let's say I pick delta 2 here. I don't even have a point for intersection because fx1 equals delta 1, which is bigger than what I want, and the left point is less than what I want, right? Because there's a jump, right, from this empty point to this solid point, and my delta 2 is somewhere in between. So I have another question. In question 1, I have infinitely many points to make this equation be satisfied. In question 2, I don't have any point. So now, we have issues, right? So this is questionable, right? According to scenario 1 and scenario 2. So we need something more general to handle those cases. That's why we have a more general version. So basically, in this general version, what we do is we take the smallest, well, actually, it's the infimum to be more precise. Infimum. So it's the limit, okay? And we want the value to be greater than the selected level. So using this general definition, what would be the quantile for the first scenario? So I write here, Q delta 1 would be x1 because I take the smallest, right? So here I will take the smallest over this interval. So obviously it's my left end point, okay? Even my left end is open, it's still the minimum point, okay? Now let's look at question 2. My Q delta 2 would be, again, x1. The reason is simple because I want, so let's analyze this set. So if I go back to the definition, we actually need this set. So let's say delta 2, right? We want all the x's such that the corresponding CDF is bigger than or equal to the given level. So I want it to be greater than this level, so it would be everything beyond x1. So here's still x. So it would be x greater than or equal to x1. And I'm going to take infimum. Infimum is the smallest, or the limit of the smallest. So that's why the smallest value, if I put infimum, then this will be x1. Okay. Under this general definition, I can get a unique quantile for any delta. Okay, it is unique because I take infimum. Infimum is unique, right? It's a more precise definition of smallest. There's no way you get two different smallest values from the same set. So this will always give you a unique result. It's the so here by this general definition, it's not only unique, you can also find it, right? So both the existence and the uniqueness are established. We actually call this the left quantile, although this concept is not important to us because we always choose this, okay? But I just want to mention that occasionally, in some analysis, it may be useful to consider the right quantile. The difference is rather subtle. So here you can see I pick greater than or equal to. Here I pick strictly greater than. There is a difference. Let's go back to the first example. Okay, so here we let delta to be delta 1, which is the constant piece, right? So now let's use this right quantile. So first, let's study this set. I want my CDF to be strictly greater than delta 1, strictly greater than. So I cannot pick anything from this flat line, right? So I will need to pick things from this, starting from x2. So that means my set, so if I take delta to be delta 1 in my example, this greater than delta 1 would be x greater than or equal to x2. So when I take infimum, this will give me x2, right? Previously, it's x1, right? And it's easy to see why I call our definition the left quantile, the other one the right quantile, right? Because the entire interval is x1 to x2. Under our definition, the quantile would be x1, which is the left point of this interval, right? If we apply a different notation, the result is x2, which happens to be the right point of the interval. So that's why this is called the right delta quantile. Okay, that is the only time I will talk about this. From this time on, please ignore the right quantile because we will never use this again. Okay, there's a nice paper by Paul Ambrose and Harvard. They wrote a nice paper to discuss quantile functions and actually beyond quantile. They discuss generalized quantile functions, which is it's very interesting mathematical paper, and there are actually a lot of applications out of generalized quantile functions. Okay, so now we are ready to define value of risk. So let the quantile be defined previously in the in this way. Okay, so we use the general definition. VaR, VAR, or value of risk, is nothing but the corresponding quantile. So when we talk about VaR, we also need to select a level delta. This is the same as the level for the quantile definition. And then VaR at level delta is just the quantile, okay? So it's the definition is pretty much self-explanatory, right? There's no need to add more explanations. It speaks for itself. Here I do have two quick remarks. First, this is rather important in the financial world because usually what we observe, when you observe the price, which we call the actual probability measure, right? So if you want to model stock price, it's often that we model the price under the real measure or actual measure or physical measure. So those mean the same thing. So this is the law under our real world. So that is P. Okay, but some of you may have heard about measure Q. Okay, which is the pricing measure. Under this measure, all the stocks, all the risky investments have the same return as risk-free. So under this world, everything share the same expected return, not the realized. Okay, because return for stocks, it's random. It can be 10%, it can be negative 10%, negative 20%, but on the expectation level, all the investment opportunities, like the stocks, futures, they have the same expected return as the risk-free account, like a saving account. That's why we call this the risk-neutral world, Q world, P versus Q. You can even Google, right? So there's actually more debate nowadays on P versus Q. Should we work on the P or work on the Q? So now the question is, we have different probability measures, right? And that obviously corresponds to probability, right? Because quantile, in a sense, it's related to the probability function, right? And the probability function or distribution function obviously depends on the underlying probability loss. Different probability loss lead to different distributions. Okay, so there's a debate on which one should be used, but this is more for the financial world. For us, it's likely we use more of the P. Another thing is when we talk about risk. So here is time 1. Here is time 0. Stands for now. We know everything at time 0. So let's say here is time 1. You have X. So loss is the random variable happens sometime in the future, right? That's the reason why those are random, because they happen in future time. At this moment, we are here. We are sitting at time 0. Okay, we want to know the loss from a particular let's say type of insurance 6 months from now. So at this point, we don't know anything, right? It's 6 months from now. So this is future. Now here's future. A question is, future is a relative concept, right? So 6 months is future. Tomorrow is also future, right? So the question is, when we calculate VaR, should we use tomorrow, 2 days from now, 3 days from now, or 3 months from now, right? So that is the question. So the T refers to the length when we want the risk to be measured, right? It can be 1 day. We look forward for only 1 day. We want to know what would be the risk for our company by tomorrow, right? Sometimes we also want to know how risky our company is in 1 week, in 2 weeks, right, etc. So the question of T is also not exactly specified in definition 7, but in practice, you must specify whether there is 1 day VaR, 5 day VaR, 10 day VaR, or any specific time frame, because that really matters, right? Intuitively, the longer the horizon, the more you want to look into the future, the more uncertainty you get, right? We have a good estimate on tomorrow's a price or tomorrow's risk, but we have no idea 10 years from now how risky this business is, right? So that's why when we calculate risk measures, usually it's for a relatively short period, and even for that, there's a debate whether you should use 1 day, 5 day, or 2 weeks, which is 10 days. So here we have more remarks. The important one is delta. Because so far delta is, technically speaking, the only parameter, right? At least that's what you can see from the definition. Delta is the only parameter. X is the underlying random variable, it's fixed. So delta is pretty much the only thing you can play with, right? And we are usually interested in big delta when delta is close to 1. That is because here in our modeling, X is the loss amount. So we want to know what is the chance that we will suffer from big losses, right? We as for companies, they don't care about the smallest losses, right? Because those do not impose huge danger to the solvents of the company, right? But however, on the other hand side, big losses, are the true danger to any company. Right? So that's why we care about big losses, and big losses also obviously means larger values of CDF, and usually we pick at least 95. Sometimes we even go with 99.5%. That means, let's say X is 1,000, not x is 1000. The quantile of 95 is 1000. The meaning is this 5% chance that the incurred loss is bigger than 1000. So from this interpretation, we easily see the economic meaning of VaR, right? Because once you know VaR, you know the worst cases, right? So if we pick 95, that means the opposite is the worst, right? So the worst five scenarios, the loss would be at least 1000. Okay, maybe bigger than 1000, but 1000 is the threshold. So it's like if you run a company and the number of policies is big enough, roughly speaking, we know 95% of the time the size of a claim is less than 1000, but there is 5% probability that the loss is more than 1000. So that's the understanding. This is what I already mentioned, right? When we calculate VaR, we need to know the time interval. Different notations. Again, this is let's ignore this slide because I don't want to confuse you. The reason I put it here is because under our context, X is the loss amount. But in the financial world, people usually use X to denote return. So if you use X to denote return, negative X is the loss, right? Because if your return is 10%, that means you are making money, right? It's the negative part. Let's say X is negative 5%. Then you have loss, right? So you have lost 5% of your money. So in that case, negative X is the loss, right? So correspondingly, you should take the negative quantile, right? And also the alpha should be small because you are looking at the left tail, right? So if you have an investment like this, okay, X is the return. This are the good side, right? When it goes to the very positive side, you are making a lot of money, right? So here is the negative part, right? This is where you make losses, and the further you go to the left-hand side, the more losses you incur, you suffer, right? So in that sense, and we know when we define CDF, it goes from left, it starts from the left, right? It accumulates from the smallest. So we look at the left tail, so the probability is small, right? So we look for small probabilities, 1%, 5%, etc. The reason we take negative is because we don't want to report negative value, okay? Even though we are losing money, for negative values, but we don't want to report negative value. We put a minus sign. The same, when you see the financial reporting, right? When they lose money, they that's usually what they do, right? That is something I quickly mentioned. More importantly, to us is to calculate VaR. How can we calculate VaR? So let's use this example. Here it's relatively easy. It's because we know. Again, that means the mean of this exponential distribution is 1 over lambda. So we know the CDF is 1 minus exponential of negative lambda x, okay? To calculate VaR, we calculate quantile. So we, delta is anything between 0 and 1. Let's solve this equation, right? Move delta to left-hand side, exponential to the right-hand side, take logarithm, and then divide by the negative delta. We get this is Obviously, this is a positive number. That's because 1 minus delta is less than 1, and the log of a number less than 1 is negative. So negative, negative, you'll get a positive number. Okay. So this is exactly VaR, right? Because VaR and quantile are the same in our definition. Next, we want to study this. Okay. VaR of this means it's log normal. So if you let y be log x, then it follows a normal distribution of mean, mu, variance, sigma square. So so let's say this equals delta. Then delta, not delta, the quantile of y would be, because this is non-standardized, so we use mu plus delta times, this stands for the, we use phi to denote the CDF of a standard normal, and then the inverse of CDF is quantile, right? The quantile is actually the inverse function of your CDF. So which means this is the, this is delta, this is not delta, this is sigma. So this is the quantile of a standard normal, okay? We already know the quantile of y, and because this is a strictly increasing function, so we just need to take exponential for y, and then we get everything we want. Finally, let's do Pareto distribution. Let's write down the CDF. Okay, now let's equate this to delta. We are trying to pretty much solve this equation. Okay, and solving this equation would be you take to the other hand side, raised to the reciprocal power. So we know the quantile will be divided by it and then minus it. Take this out. So we need to divide, so the power becomes negative, -1. Okay, as you can see, for distributions, well, you are able to derive the CDF. Then finding VaR is equivalent to solving an equation. Okay, in some cases you can get an explicit form like A and C. Sometimes you can't solve it explicitly. You will need to use some mathematical notation to express it, and then later on apply numerical methods to calculate the final result. Nowadays, we have a lot of software like R. You can easily calculate this value, right? Then you can compute the VaR for a log normal distribution. Next, let's do another example. Well, you have discrete. So example 4 is discrete. The distribution is given by this. Okay, it's given below. What I would suggest you is write down the CDF, because when we define quantile or when we define value at risk, we use an equation of CDF, right? So the first job is usually to figure out the CDF. So this part is easy, okay? When x is 0, probability is 0.8. So it's up until the next jump point, which is 50, right? This is a discrete. So once I jump at 0, I will remain at that level until the next jump. The next jump is 50. That's why here I put less than, but I do not include equality, because when x equals 50, I'm going to jump up again. okay, until my next one. So it is cumulative, right? So you start with 0.8 and then you plus 0.12. That's why I have 0.92 for the for this piece. Okay, next I add another probability at 80. Okay, it will remain that at that level until 90. At 90, I jump again by 2%. Okay, I remain at 98 until x is 100. Beyond 100 is 1. Okay, that is the complete piece. Okay, complete definition of CDF. Now let's do the analysis. For 95. So again, I want the value to be bigger than 95. Okay, bigger than 95. Okay, which means this has to be greater than 80, right? Because this is the first value of your CDF that is greater than 95%, right? And the corresponding x is x greater than 80, right? Of course, beyond 80, it's always bigger than 95. So it's 80, right? Next, 96, right? It is the same. It is still greater than or equal to 80, so it is still 80, 80 as the quantile. 98. So I want my CDF to be greater than 0.98. So it's at this level, I need my x to be greater than or equal to 90, and the infimum is 90. Finally, I want 99%. So I don't have anything bigger than 99 except the last piece. Okay, this covers a lot of scenarios, right? For example, 95 is between 92 and 96, and I need to go up to the next level. Instead of 50, I will need to go to 80 because I want something greater than or equal to the given level. Okay, so I will need to always go enough, make sure the level is enough, is well satisfied. That should give you a basic idea of how you can calculate VaR. But of course, I can also give you a continuous random variable, right? And then your first step would be to do an integral. So again, I assume this is a non-negative random variable because we work with losses, right? So I think I will end here for the introduction part of VaR. In the next video, we're going to do something slightly more complicated for VaR. It's the properties of VaR.